Plunging into the vessel space, Proxima B is an additional planet in the habitable zone of its star, Proxima Centauri, with a composition remarkably close to Earth's. This star is noteworthy because, after the Sun, it is the closest star system to our own. This red dwarf star is an intriguing subject for astronomical research because it is 4.23 light-years away from our Sun. Both scientists and amateurs are interested in Proxima B because it has circumstances similar to those on Earth. Astronomers have recently been able to detect lights coming from the exoplanet Proxima B thanks to technological advancements, especially the new James Webb Space Telescope. This discovery could provide strong evidence that the planet is inhabited by extraterrestrials, sparking interest and curiosity about the possibility of life beyond our planet. But there are a ton of other fascinating discoveries that the James Webb Space Telescope may provide for humanity, this being just one. The possibilities of discovering fresh information on Proxima B with our powerful telescope prompt significant doubts regarding the viability of sending a manned expedition to this far-off exoplanet. As we continue to explore this intriguing finding by James Webb, stay tuned. Consider subscribing to our channel if you're passionate about staying up to date with the latest discoveries about the cosmos and all of its wonders. To remain updated, don't forget to like this video and activate the notification bell. What precisely is an exoplanet, then? A planet that orbits a star other than our Sun, or one that lies outside the confines of our solar system, is referred to as an exoplanet. Proxima B is one of the exoplanets that has generated the most attention among scientists studying exoplanets. Proxima Centauri, the star that is connected with Proxima B, is categorized as a red dwarf due to its relatively cold temperature of 2,872 degrees Celsius. It is roughly 500 times less bright than our Sun and much less big. Proxima B must be close to its star in order for life as we know it to exist there, as it is located in the habitable zone. This is usually the region on a planet's surface where liquid water, an essential component of life, can exist. Proxima B bears several striking similarities to Earth, including its continents, oceans, and possibly even life itself. Because of the strong flares that the planet's star emits, the planet's atmosphere may seem green due to the existence of auroras. The complicated magnetic environment produced by these star flares may give rise to unusual atmospheric phenomena. Remarkably, Proxima B is tidally locked, which means that, like our moon orbiting Earth, the same side of the planet always faces its star. This creates a twilight zone, where perhaps life is more suited to survive. Proxima B's surface temperature may vary greatly, from -90 degrees Celsius to 30 degrees Celsius, resulting in a diverse spectrum of habitats. Around 11 Earth days are needed to complete one full orbit around Proxima Centauri, indicating a far shorter year than ours. Furthermore, Proxima B has a gravity that is roughly 1.3 times stronger than Earth's, which could have an impact on any future life forms that might arise there. Still, scientists are unsure about Proxima B's atmosphere's precise composition. If it exists, it might include elements that are necessary for the metabolic processes required for life, like water, different minerals, and carbon dioxide. Proxima B is the subject of much enthusiasm, but because of its great distance, sending manned trips there is still a major hurdle. Nevertheless, billionaire Yuri Milner is funding the development of a concept called Breakthrough Starshot. The goal of this project is to develop nanoprobes that can move at 20% the speed of light. These probes would be built to travel to Proxima Centauri, providing a once-in-a-lifetime chance to conduct in-depth research on our nearby star system. With their estimated speed of 16,000 kilometers per second, these nanoprobes should be able to get to Proxima Centauri in a few decades. Future generations could benefit greatly from such a trip, which could reveal mysteries about Proxima Centauri and its fascinating exoplanet Proxima B. When these nanoprobes do come, who knows what they might find? Interestingly, Proxima Centauri has already started to send us signals. Astronomers, including Anderson from the University of California, were interested in the star because it was putting out very powerful flares, which the park's radio telescope picked up on during its studies. In order to learn more about whether or not we are the only technological civilizations in the cosmos, he oversaw the Breakthrough Listen project. This program is a component of the larger SETI, Search for Extraterrestrial Intelligence, effort. As part of the project, different signals from space are gathered and stored in order to build a database for later study. Significant findings have been made from the data gathered, especially since UC Berkeley student Shine Smith began studying the signals. A peculiar narrow-band radio frequency emission at 982,000 MHz that was concealed in the Proxima Centauri measurements was discovered by him while he was working. Sophia Sheikh of Penn State University became interested in this intriguing finding and took over the signal analysis. She said that because it differs from the usual patterns we have seen in the past, this signal is one of the most exciting discoveries of the Breakthrough Listen project. Signals are detected by the Parkes radio telescope during intervals of 53 minutes. In order to verify that any possible signals are from Proxima Centauri, the telescope points at the star during these sessions and then moves to study other parts of the sky. After around 3 hours of observation, according to Sophia, a signal was reliably received 5 times every 30 minutes when the telescope was pointed toward Proxima. On the other hand, the signal disappeared as the telescope moved away, posing fascinating puzzles regarding its origin. This highlights how important the discovery is. The observation of this kind of non-earthly signal, according to astronomer Dear RIT of the University of Pennsylvania, strongly implies the existence of advanced technology. With the help of the James Webb Space Telescope, which is aimed toward Proxima B, ongoing analysis of these signals seeks to confirm their extraterrestrial origin. It is anticipated that the telescope will soon be able to detect artificial light from the planet, offering more proof of a potential civilization. Abraham L. from Harvard University underlined that the James Webb spacecraft could detect artificial nighttime illumination from Proxima B with an unprecedented 85% certainty, provided that the light's intensity reached 5% of that of natural daylight illumination. Because Proxima B is much smaller and fainter than our Sun, its habitable zone is not shaped as it is. The habitable zone is significantly closer to the star than it is in our solar system because of this special property. With an orbital period of roughly 11.2 Earth days, Proxima B orbits Proxima Centauri at a distance of about 4.5 astronomical units. Proxima B's potential habitability may be jeopardized by Proxima Centauri's violent solar flares, which are known to be extremely active. The exoplanet's close proximity to its star also causes drastic temperature differences, with the day side being extremely hot and the night side being extremely cold. Significant alterations in temperature may have a significant impact on the planet's capacity to sustain life. Because so much information has been obtained about it, Proxima B is the exoplanet that astronomers and academics are most interested in studying. It is not the only exoplanet, though, that shows characteristics similar to Earth that could be home to life. There are still many more exoplanets to find, but so far only 55 possibly habitable exoplanets have been confirmed within the Milky Way galaxy. We are still looking for and identifying these far-off planets even as our technology develops. For example, there is still a great chance that there are livable or inhabited planets in the similarly sized Andromeda Galaxy, our neighbor. More options are also provided by superclusters of galaxies within the greater framework of the universe. As a component of the local supercluster, which is made up of about 100,000 galaxies, the Milky Way is a member of the local group, a cluster of about 40 galaxies. Surprisingly, calculations indicate that there are approximately 10 million superclusters in the universe. This prompts some serious reflection. Given that the Milky Way is only a small galaxy with 55 proven possibly livable planets, just think of the uncountable number of habitable planets, or perhaps life, that exist throughout the infinitely vast observable universe. Finding exoplanets is important because it may help us better comprehend how we fit into the universe and provide important answers to basic queries of life and existence beyond Earth. We can examine the great diversity of planetary systems and consider the possibility of extraterrestrial life as a result of the continuous study of exoplanets. Furthermore, these findings may improve our understanding of the formation and evolution of planetary systems. The ramifications for the hunt for alien life are significant. Exoplanets are important contenders for supporting life and can reveal important details about the environmental requirements for life to exist elsewhere. In the end, studying exoplanets helps us test the hypotheses and models we currently have about the genesis and development of planets and star systems, greatly expanding our knowledge of the cosmos and our place in it. Human curiosity has long been piqued by the vastness of our cosmos, leading us to look for explanations for both our existence and the possibility of life elsewhere. In addition to being a scientific undertaking, the search for new worlds raises philosophical issues that cast doubt on our conceptions of life, habitability, and the universe in general. Our tools and methods are becoming more advanced as we explore farther into space, giving us access to previously unthinkable insights. Recent space missions to a variety of solar system planets have yielded insightful information on their planetary ecosystems. For instance, evidence of ancient rivers and lakes has been found by the Mars rovers, indicating that the red planet may have once supported circumstances conducive to life. Furthermore, missions to the outer planets, like the Cassini probe examining Saturn and the Juno spacecraft orbiting Jupiter, have provided detailed information about their atmospheres, magnetospheres, and moons, some of which may potentially support life. The variety of different habitats demonstrates the numerous ways that life could possibly emerge. The quest for exoplanets has fundamentally changed our perception of potential habitats for life. Thousands of exoplanets have been found by Kepler's mission alone. Many of them are found in the habitable zones of their stars. Thanks to these discoveries, the concept of a potentially habitable world has been widened to take into account a number of variables, including the existence of moons, the makeup of the atmosphere, and geological activity. The idea of biosignatures, or signs pointing to the existence of life, is one fascinating facet of the study of exoplanets. Scientists are working on methods to examine the atmospheres of other planets, searching for chemicals that may be signs of life activity, such as carbon dioxide, methane, and oxygen. Astronomers are getting excited about the prospect of searching for biosignatures with observatories such as the Roman Space Telescope or the Future Extremely Large Telescope, ELT. These findings have the potential to fundamentally alter our knowledge of the universe's distribution of life. Apart from first-hand observations, the study of astrobiology has gained momentum, exploring the potential environments that could support life elsewhere. To learn more about the boundaries of life, scientists are examining extremophiles, or organisms that can thrive in harsh conditions seen on Earth, such as acidic lakes and deep-sea hydrothermal vents. Our quest for life in previously thought to be inhospitable locations, including the frigid moons of Jupiter and Saturn, is informed by this research. Particularly intriguing are the subterranean seas on Enceladus and Europa, which may be home to microbiological life. The prospect of populating other planets seems more and more likely as time goes on. Human traveling projects like NASA's Artemis program and SpaceX's Starship anticipate a long-term human presence on the Moon and beyond. These programs seek to not only push the edge of human exploration, but also create a lasting human presence in space, opening the door for future research into the solar system and beyond. There are important philosophical and ethical issues that arise from the possibility of finding life elsewhere in the universe. If humans came into contact with extraterrestrial life, what would that mean? How would we go about interacting and communicating with sentient beings? These are not just hypothetical questions, but rather important ones to take into account for upcoming missions. Scientists and ethicists alike are becoming more interested in creating frameworks for moral interaction with alien intelligence. Furthermore, our comprehension of planetary systems is put to the test by the ongoing discoveries in the field of exoplanet research. Current models of planet formation are complicated by the existence of uncommon planetary configurations, such as hot Jupiters, which are gas giants that circle extremely close to their sun. Scientists are compelled by these anomalies to reconsider the dynamics of planetary migration and the impact of star interactions on the evolution of planets. Another idea under review is the idea of the Goldilocks zone, an area where conditions are ideal for life. Studies suggest that a wider variety of environments may support life than previously believed. Subterranean oceans atop ice sheets, for example, may offer stable habitats for life, and high-energy environments, like those around black smokers on ocean bottoms, may also support distinct biological systems. The stunning photos from telescopes and the motivational stories of space exploration missions, such as the James Webb Space Telescope and the Perseverance rover, have greatly increased public interest in space exploration. Through social media, scientists may interact with the public and share their research, creating a global community of astronomy and exploration enthusiasts.